Good morning. I welcome you all to the series of lectures on thermodynamics. Today we are going to discuss about the thermal energy reservoir, heat engine, representation of heat engine, heat pump, heat pump, representation of heat pump, and the refrigerator, and the representation of refrigerator, and the relation between COP of heat pump and the COP of refrigerator. Now just look into the thermal energy reservoir. Simply the definition of energy reservoir, thermal energy reservoir is it having infinite heat capacity. By giving or losing heat, its temperature will not change. That means thermal energy reservoir is a infinite heat capacity device. It having infinite heat capacity. By giving or losing heat, its temperature will not change. That is the statement. Now, high temperature reservoir is called source, low temperature reservoir is called sink. There are two types of reservoirs we have, source and sink. Out of that, high temperature body is source, low temperature body is sink. Now, examples for source: boiler, furnace, IC engine, nuclear reactor. These are the examples for source. Next, examples for sink: atmospheric, air, river. These are the examples. Now let us define the heat engine. It is a device which is used to convert heat energy into mechanical work. Heat engine is a device which is used to convert heat into mechanical work. So examples: IC engine, steam engine, turbines, all. Representation of heat engine. This is the representation of the steam, heat engine. So this is the source, this is the sink. When heat is this source temperature is T1, sink temperature is T2, T1 is more than T2. When heat is transferred from high temperature reservoir and transferred to low temperature reservoir, in between if I place the engine, so engine is taking heat from high temperature reservoir and convert part of it into work, that is W net, that is nothing but Q1 minus Q2. So the some amount of heat is rejecting as it is, some only part of this heat energy is converted to work. If this total heat energy is converted to work, then the efficiency of the engine is 100%, because conversion is 100%. So that is the efficiency, but the efficiency never be 100%. So that means there must be some there must be some rejection. When efficiency is good 100, it is ideal machine. All the time there must be some reduction in efficiency, that should be less than 100. So by an amount of heat rejection Q2. So this is the sink T2. Now thermal efficiency is equal to work output by heat input. What is the work output? W net. Heat input is Q1. So W net is Q1 minus Q2 by Q1. So efficiency equal to 1 minus Q2 by Q1. For example, if Q2 is 0, for example Q2 is 0, there is no heat rejection. So then Q2 is 0 means 1 minus 0, 0, 1 minus 0, 1. That is efficiency is 100%. Okay, because the efficiency never be 100%, because there must be all the time some heat rejection. Okay, it cannot convert the 100% heat into it cannot convert the heat into 100% work, because low grade energy never converted into high grade energy 100%. Okay, the next one, representation of the refrigerator. See, it is a device operating in a cycle, maintains a body at a temperature lower than the surroundings. See, this is the device which is used to maintain a body at a temperature lower than the surroundings. Means, see, this is the refrigerator, or it is taking heat from low temperature body and supply heat to high temperature body. For example, this is the sink. Sink is nothing but a room. For example, in the summer, what we need to do? We need to make the room cool below the atmospheric temperature. In this situation, we need to take heat from the room and supply to atmosphere all the time. For that, we place refrigerator in between the room and the atmosphere. So this refrigerator is taking heat from the room and supply to atmosphere. So this amount of, this is the representation is same all the time. This is source at the top and which temperature is T1. This is the sink whose temperature is T2. T1 is more than T2. In the earlier case also T1 is more than T2. In the engine case also, don't get confused friends. Source, sink, T1 same T2, T1 is more than T2. Q1, see, heat is related to T, whatever the heat that is related to temperature, that is all the time same suffix 1, 1, 2, 2. Okay, don't get confused please. Now Q1 amount is connected to T1, Q2 is connected to T2. Now this room temperature, we want to maintain this room temperature below the atmosphere, so that for that we need to take all the time heat from the room and supply to the atmosphere. In between, what I do, I place the refrigerator. So for that refrigerator, to run the refrigerator, we need to give work input to the system, because refrigerator is a work consuming device. So if you want to take heat from low temperature body and supply heat to high temperature body, you need to give work input to the system. Now it is taking Q2 amount of heat, and by taking some amount of W work, it is converted into heat. W is also, some amount of W is also converted into work, and this work and heat together form the heat, and it is sent to the atmosphere as Q1. Now, so coefficient of performance, COP of the refrigerator, is desired effect by network input. See here, the desired network input means W. See, desired effect is nothing but a amount of heat. There are two amounts, there are two heats we have, Q1 and Q2. But what is the desired effect? As a refrigerator, what is the function of the refrigerator? Taking heat from the low temperature reservoir, that is Q2. See, amount of this desired effect is equal to amount of heat extracted from low temperature reservoir, that is this one. Q2 is the desired effect. Q2 by network input is the Q1 minus Q. W, that is Q1 minus Q2. Q2 by Q1 minus Q2. Now the representation of the heat pump. It is a device, it is reverse to the refrigerator. It is a device operating in a cycle and maintain a body at a temperature higher than the surroundings. Means this is the heat pump. See, this is the source, this is sink, T1, T2. T1 is all the time greater than T2. Don't get confused, friends. All the time notation is T1 is greater than T2. Source is at the top, sink is at the bottom. Okay. This T1 is connected to Q1. This Q2 is connected to T2. Now we want to maintain a body at a temperature higher than the surroundings. That means in the winter, what we need to do, we need to maintain our room temperature more than the surrounding temperature. Further, what we need to do, we need to take heat from the surrounding and supply to room. So this room is the now source, because we are taking heat from the sink, that is atmosphere. In the winter, we are taking heat from the atmosphere and supplying heat to the room. So then only our room temperature is maintained more than atmospheric temperature. Now see, coefficient of performance, COP of heat pump equal to desired effect by work input, formula same. But the desired effect is, there are two heats we have, Q1 and Q2. What is the desired effect? See, desired effect is how much amount of heat is supplied to the room. That is the desired effect, because to maintain the room temperature more than surrounding in the winter, how much amount of heat is entering into the room, that is the desired effect. That is the main effect we want. Desired effect equal to amount of heat supplied to high temperature body. So COP of heat pump equal to, see, desired effect is Q1, work input is W, that is Q1 minus Q2. Now relation between COP of heat pump and COP of refrigerator. COP of heat pump is equal to, already we know COP of heat pump as Q1 by Q1 minus Q2. COP of refrigerator as Q2 by Q1 minus Q2. Then we can write, so COP of heat, I just take this term, COP of heat pump minus COP of refrigerator. Then what I get, COP of heat pump as Q1 by Q1 minus Q2 minus COP of refrigerator is Q2 by Q1 minus Q2. Q1 minus Q2 is common in the denominator, so automatically the numerator also Q1 minus Q2 is equal to 1. Then COP of heat pump minus COP of refrigerator is 1. Otherwise you can write COP of heat pump is equal to 1 plus COP of the refrigerator. In some problems, they will definitely ask, they will give you one COP. That means they may give you COP of heat pump as 4. Then they will ask you to find the COP of the refrigerator without giving any data. Then they will ask you directly, COP of refrigerator is how much. Then it is simply, this is 4, then automatically this is 3. COP of refrigerator is 3, you can answer directly. Thank you very much.